Right holder. Okay, shall we? So the next step I would like to do in this lecture series is sort of connect up my lectures with the lectures of some other speakers. Namely, we would like to use Heegaard Floer theory to examine contact structures, and the path will lead through open book decomposition, so it will, we are all connected. But before doing that, let me just give you a very brief sort of summary of the properties I would like to use from Heegaard Floer theory. So the way you should treat these statements is like, so when we learn homology theory, the decent way to do it is go through singular chains and all these technicalities. The sort of shorter way to do it is going through the Eilenberg-Steenrod axioms. So what I will do now is I will list the proposed Eilenberg-Steenrod axioms for Heegaard Floer homology. Of course, there is no real content behind that, so they not uniquely specify Heegaard Floer theory, but at least these are the properties we will use. So let me just very quickly go through the theorems. Most of them should be familiar from Peter's and Zoltán's lectures. Some properties might seem new, and then I would like to spend more time with them. So first of all, what is the setup? So we have a spin C 3-manifold. Then Heegaard Floer theory associates to it. So first of all, I will only use the hat theory, and the coefficient will be Z2 for me. So this is a finite dimensional Z2 vector space. So for a spin C 3-manifold, we have a finite dimensional Z2 vector space, and if we have a spin C cobordism, that means that X is a cobordism between two 3-manifolds Y1 and Y2, and the spin C structure S restricts to T1 and T2 on the two ends. Then the theory assigns a map which is just a linear transformation from one end to the other. Well, hopefully you can just guess what I wrote there, probably don't see. So F is just a map from the Heegaard Floer group of Y1 with spin C structure T1 into the group of Y2 with spin C structure T2. And there is a convention which is the following, that when you see HF hat of Y by itself, then what I mean is just the sum of all these groups for all the spin C structures. And you have to remember there might be infinitely many spin C structures, but luckily this is still a finite dimensional vector space, since the chain complex from which we derive has only finitely many generators. Those are the intersection points of T alpha and T beta. So this is still finite dimensional. And when I write Fx, what I really mean by this is the sum of all maps for all spin C structures. And it is less clear that we still have a finite sum here, but let me just give the first sort of property, which is called the adjunction. So there are two parts of it. There is an adjunction for 3-manifolds, and there is an adjunction for 4-manifolds. One was already mentioned by Peter. The second one did not appear yet. So the statement is that if HF hat of YT is non-trivial and sigma is a closed surface in your 3-manifold Y, then C1 of the spin C structure T evaluated on the homology class of sigma is either 0 if the surface is S2, or less than minus chi sigma if it is not. So somehow you immediately see that there is a strong relation between the possible non-trivial Heegaard Floer groups and the geometry of the underlying three-manifold Y. And the B part of the adjunction formula is a statement for four-dimensional cobordisms and the maps, and it goes as follows. If sigma is a closed surface in a cobordism, and the map is non-trivial for some spin C structure S, then again we can do the same game. We can just evaluate C1 of the spin C structure in sigma, but now we have an additional term, namely we can take the self-intersection of the homology class represented by this surface, and again the conclusion is the same. This is 0 if sigma is S2 or less than minus chi of sigma otherwise. So we have, shall I flip the blackboard? So this immediately tells you that there might be only finitely many spin C structures for which the map is non-zero. So this sum is eventually a finite sum, and we get fx mapping from the corresponding age fy1 to age fy2. Okay, so these are sort of the first important properties of these maps. Let me just list some sample computations. We essentially went through these in one of the previous lectures. So the first is, what is HF hat of S1 cross S2 with the trivial spin C structure? Remember, the spin C structures always have a C1 invariant, and let's take T0 to be the one which evaluates, which has C1 equals 0. And the statement is that it's just Z2 plus Z2. If you think about this picture of taking the Heegaard decomposition of S1 cross S2 with one alpha curve and the other beta curve should go like this to have an admissible Heegaard decomposition, then you actually see the two generators. HF of a length space LPQ with any spin C structure is actually Z2. There is only one intersection point, and remember, we always use Z2 coefficients. So in particular, HF hat of LPQ, just to practice the terminology, is Z2 to the P, which might sound as a disappointing fact, because somehow it shows that, you know, the length space is given by two pieces of data, and only one is recorded in the Heegaard Floer group, but that's only an illusion. We will see that somehow the Q will appear in some further data. So what happens if we take a connected sum? Let's take the connected sum of two three-manifolds equipped with two spin C structures. This happens to be equal to the tensor product of the two Heegaard Floer groups over Z2, and this should resemble you to the Q-net formula, and the way to prove it is actually the Q-net formula. And one more statement is that how to relate the Heegaard Floer group of Y to the Heegaard Floer invariant of minus Y. And the answer is that you get isomorphic theories, and the philosophy behind it is that somehow Heegaard Floer homology of minus Y is eventually the Heegaard Floer cohomology of Y. So when you have a chain complex, you have to make a decision whether you compute homology or you take the hom functor and you turn it into a cohomology, and eventually this is sort of the cohomology of Y, and working over a field coefficient Z2, we have this Poincaré duality. Okay, so these are the sort of basic facts we will need. And then the next sort of group of statements is degrees and degree shifts. Which says that, so, we are talking about homologies. And so in homology, you got used to the fact that there is like first homology group, second homology, and so on. So there is a grading. And in fact, for Heegaard Floer groups, we still have a grading. But the analogy is not that nice as you might expect. So for example, the grading does not always exist as an absolute grading, and it might not be an integer. So here are the statements. So this is D, says that hf hat of yt is a relatively z over dtz graded group. So somehow we cannot talk about the actual grading of an element, but we can talk about the grading difference, and this is still not well defined, only mod this number where dt is the divisibility of C1 of the spin C structure as an element of the second cohomology. Now, if dt happens to be 0, meaning that C1 is a torsion element, if C1t is torsion, then actually we have a relative Z grading on the group, and there is a statement of Peter and Zoltan, and Peter sort of indicated the statement today. Then there is a lift of this relative Z grading to an absolute Q grading. So it takes time to get used to the terminology. So a relative Z grading means that you cannot talk about the grading of individual homogeneous elements, but you can tell the grading difference, and this should be an integer. And the lift of such means that eventually we can assign a rational number to each homogeneous element such that the difference of these rational elements is exactly the relative Z grading. So this is the best we can do here. And so this is what we can say about the degrees. And now the degree shift. I just repeat the formula given by Peter today, saying that, what to say. So if T1, T2 are torsion spin C structures on Y1, Y2, then the degree shift of generated by Fxs. So we have a spin C cobordism between the two spin C 3 manifolds. Both come with an absolute Q grading. And the question is, you take a homogeneous element and it maps to another homogeneous element. What is the difference between the gradings? Is equal to 1/4 C1 square S minus 3 signature of the 4 manifold minus 2 times the other characteristic of the 4 manifold. So this is the quantity with which you shift the grading. Sometimes it's sort of quite tedious to compute, especially as opposed to what one would expect as a square of a second cohomology element. This is not an integer. This is just a rational number, because C1 is not compactly supported as it's given, only its high enough multiple. If the restrictions are torsions, then high enough multiple will be compactly supported, and for that the squaring makes perfect sense, but then we have to divide back with the number we just multiplied it to become compactly supported. Any questions? So this is sort of recollections, but still we have a question.
Exact assumption B, that X is closed, and so F makes...
Oh, no. Sigma is closed. X is a cobordism. Sorry, so... Yeah, actually, there is always this trick. If you have a closed 4 manifold, then you just delete 2 points. But here what I meant is that if there is a closed surface in a 4 manifold with possible boundaries, then we have this inequality. Okay, so this is E. Now comes a sort of a new one, conjugate action. So we might need to spend a little more time with this. So there is a Z2 action on spin C structures sending T into T bar, which I will describe in a few minutes, inducing isomorphism JY from HF hat of YT to HF hat of YT bar. So there are somehow spin C structures are paired up in some way, and the corresponding Heegaard Floer groups happen to be isomorphic. And in fact, if it makes sense, by this I mean that T is a torsion spin C structure, meaning that its first Chern class is torsion, and we have an absolute Q grading, then in fact this JY is an isomorphism between the corresponding degree D homology elements. So let me just spend some time talking about this conjugate action. So let me just recall what the spin C structure was. So recall spin C structure is just the same as an equivalence class of nowhere vanishing vector fields and you remember the equivalence is being homotopic outside of a ball, which is of course the same as equivalence class of two-plane fields. Here the equivalence is just you take a two-plane field and you can take its oriented orthogonal, and this will give you an over-vanishing vector field and vice versa. And so the conjugate action is quite easy to describe in these two languages. So suppose that T, the spin C structure, is given by the equivalence class of a vector field, V, nowhere vanishing vector field, or in the two-plane field language with a two-plane field Xi, oriented two-plane field. So this is a vector field, and this is an oriented two-plane field. Then the conjugate action is quite simple. Then T bar is just the equivalence class of minus V. So we just multiply by -1 the vector field, which corresponds eventually to Xi bar, the same two-plane field with the opposite orientation. Or, an oriented two-plane field is in fact a complex line bundle, and we just take the conjugate complex structure on the line bundle. So this is where the name comes from. But this is why it's a conjugate action. Let me just spend 2 more minutes about sort of connecting to the various definitions of spin C structures. It might be helpful to see one special feature. So remember, this was the definition what Peter was using, but earlier last week, Ron was giving us sort of a more homotopy theoretic definition, namely if you have a manifold, say a 3 manifold, and we have its principal SO3 bundle. This is like the frame bundle, which is, to confuse things, it's a trivial bundle. And the question is whether can we lift it to a PU2 bundle. Whenever we can make such a lift, we have a spin C structure, and the different lifts correspond to different spin C structures. So such a lift is eventually a spin C structure. Now, how do these two things relate to each other? So what is the problem? We have SO3 as a structure group of this manifold, of this bundle, and we have the natural S1 fibration over SO3 given by U2, the group U2. Now, if we just happen to have the co-cycle structures here, then there is no unique way to lift it. But because the bundle is non-trivial, as you can check. Actually, it's a good thing to check that there are two bundles, two S1 bundles over SO3, the trivial one, and this is the other one. You can just check it by computing H upper 2. So, as it stands, it's unclear how to lift the co-cycle structure of the frame bundle to a U2 bundle. But notice, if you have a two-plane field, it just reduces the structure group to U1. So a two-plane field just gives you this reduction. And of course, to lift from U1 to U2, that's not such a hard thing. You just take an element lambda here, and you send it to lambda 0, 0, 1. So whenever you have a two-plane field, it just gives the reduction of the structure group for which there is a natural lift. So this is how the correspondence goes. A two-plane field induces a spin C structure in the old sense, in this natural way. And of course, it's not very hard to go in the opposite direction if you have a U2 bundle over Y, which means that two-dimensional complex vector bundle over a 3-manifold, you always have a non-vanishing section of it. And this means that this structure group, in fact, can be reduced to U1. And you just project back. There is one point I would like to make. So one might ask, so first of all, C1 of the spin C structure is the same as C1 of this two-plane field, which is the same as C1 of the corresponding C2 bundle. And we might ask, what does it mean, this invariant to vanish? So let me just keep going here. Okay. So C1 equals 0 means that in fact this lift can be homotoped from U2 into SU2, right? C1 is just the obstruction to homotope the co-cycle structure of this bundle into SU2. So this means that the co-cycle structure of the spin C structure can be homotoped to SU2. And I think I forgot to tell you what the role of U2 is in this story. So this is simply just spin 3, and SU2 is just the third spinor group. So this just shows that C1 equals 0 means exactly that our spin C structure is in fact a genuine spin structure. So T is spin. And I hope it is familiar that, you know, the spin structures on a manifold are in one-to-one correspondence with the elements of the first cohomology with Z2 coefficients. And notice in this conjugate action, it's sort of easy to see that C1 of T bar is minus C1 of T. And with a little bit of trickery, you can just convince yourself that C1 equals 0 is equivalent to say that T is its own conjugate. So let me just write that down. Right here. So T is spin if and only if C1 of T is equal to 0. And somehow, you know, it's just a digression. There is no Heegaard Floer or any frightening holomorphic gadgets. It's just pure good old homotopy theory. And the same story can be done for the four-dimensional manifold, and I will not go into the details of that. I just give you the statement. So for a four-manifold X, there is again sort of a geometric approach to spin C structures. So a spin C structure S is a spin C structure. S is a suitable equivalence class of almost complex structures defined on X minus X1 Xn. So by this I mean that spin C structures are like equivalence classes of almost complex structures which are not defined on the whole manifold X, but away from finitely many points. And I don't want to go into the description of what the equivalence classes are, but you can see that in a similar manner as before, we can associate a C1 to a spin C structure. Notice that two cohomology classes on a four-manifold are not really sensitive for deleting a couple of points. They extend uniquely. And we get the same kind of J action, the conjugate action, by taking the conjugate almost complex structure on X. So this approach provides the J, or this conjugate action from S to S bar, with the property that C1 of S bar is minus C1 of S, and C1 of S is equal to 0 if and only if S is spin. So somehow the advantage of having spin as opposed to spin C is that there are too many spin C structures. Typically there are infinitely many. You know, if B1 of the manifold is non-zero, then you have infinitely many. But spin structures you have much less. And this will be sort of a theme we will pursue on and on. So I thought it's a good thing to start worrying about what these spins are early enough. Well, let me just finish the conjugate action story. So as we see, there is a conjugate action on the three-dimensional level and on the four-dimensional level. And of course, there is an equation relating the two. So I didn't finish F, and I did finish F, but I didn't start G. And it says the following, that Fxs, so if you have a spin C cobordism, then the induced map is the same as you first apply the isomorphism on the conjugate isomorphism on Y1, and then you apply X with the conjugate spin C structure, and then we apply Y2. So somehow, you know, conjugate of the conjugate is the same as doing nothing, or something like that. So you work it out. Probably I could put this guy into the other side, and then it would be like the D-bar equation. Okay. So I should make the point that, so we sort of, I wrote down a couple of properties of Heegaard Floer theory. And until now, the real hard part was the first statement, that this functor exists and it's well defined. And the rest is sort of much less complicated. And as the finish of this part of the lecture, I would like to give you this main computational tool Peter just lectured about yesterday and today, namely the exact triangle. And the reason I would like to tell it to you is that there is a refined version of that, and we will make use of that, so I just would like to make it clear how it goes. So the last bit is surgery exact triangle. And let me just give you my version the way I usually write it. So start with a three-manifold Y, and there is a knot inside with some framing. It doesn't have to be a number. It's a framing, meaning that there is a nearby knot. And we attach a two-handle to Y, or Y cross I, along K with framing F, and we get a new three-manifold YK. If Y is presented by a surgery diagram, then what you do is you add one more curve to the surgery diagram. So I will just denote it by this dotted K with framing F. So somehow, you know, the way you should think is that Y is given by a surgery diagram, all solid curves. And then you add the dotted one, which means that you have the three-manifold given by the solids, and you add one more two-handle represented by the dotted. And you get to a new three-manifold. And then we get to F. So this is what Peter called this, right? By doing the following, that now YFK is represented by the old solid curves plus one more new solid curve. And this cobordism, this is what I will call X1, this is X2. This new cobordism is just simply given by attaching a two-handle along the boundary of a normal disk with framing -1. Now it became a number because there is a reference disk, right? The spanning disk of this circle. And then there is X3, which is, now we have more curves when we represent this guy, and we add one more. Of course, in this triangle, there is a statement packed in that if I do it twice, so I add K, then a -1, and then a -1 again, then I get back to where I started from. And it's not hard, but I learned something yesterday that I will not do it, okay? Actually, you just do a roll and twist here, but let's keep it as our secret. Okay, so this is what we call...
that doesn't kill K, though. You have to give it K.
It does. Homework. You just pull it down, then it becomes a 0. And then you flip it over with a slam dunk, and it will pick up an infinity framing. Yes, so I am not, as you could see. So the point is that we have this surgery triangle. There are no Heegaard Floer groups, but luckily it induces something on the Heegaard Floer groups and the maps. Namely, it gives this triangle. So this induces HF hat of Y fx1, HF hat, YFK, HF hat, YF plus mu K, and the statement is the theorem is one word, exact. And let me just go very quickly into the refinement I was promising, I promised, namely that in fact this triangle is somehow the sum of many independent triangles. Let T be a spin C structure of Y minus neighborhood of K. So this is now a three-manifold with boundary, and let's fix the spin C structure on this side. This three-manifold is a subspace of each and every one, right? Because what we do, we just take out the neighborhood of K and we glue back in 2 different ways, or in 3 different ways to get Y back, and this guy and then this guy. And so let's define Ty to be those spin C structures, T tilde, which restrict to this given one. And then I leave you to your fantasy how to define T of Yk, of Yfk, and so on. And then the statement is that we have an exact sequence and I don't want to write down the maps. So these are, I just indicate the first one. So we just take x1, and now we are not taking all the spin C structures. We just take all those spin C structures which extend the 2 boundary spin C structures. So we just take all spin C cobordisms which can arose in this triangle. And again, the statement is that this is exact. Okay. Any questions so far? So let me just make a historic comment. So somehow yesterday's proof of the triangle might seem to be sort of complicated. So first of all, you should see the original proof of Peter and Zoltan, and then you will change your mind. And the second is, what you have to know is that somehow the idea of searching for triangles was around. It was actually the idea of Floer in Donaldson theory. And when Seiberg-Witten theory was started, then people tried to prove the exact triangle, and they couldn't succeed it. So, this happened in '94. This is when Witten came out with the new equations, and from '94 until 2003, we just couldn't prove it. I mean, we meaning that they, I mean, the smart guys. I didn't even try. But so, until 2003, there was no triangle for Seiberg-Witten's theory. There was a triangle in Heegaard Floer, and this was sort of the big advance. But then Peter and Zoltan figured out a new way of proving the exact triangle in their theory, and this new proof, what you just heard yesterday, just straightforwardly generalizes to the Seiberg-Witten case. So just, to give the proper credit, I think we should keep this in mind. And now I would like to spend some minutes on applying the triangle and to show you how easy life becomes when you know the triangle. Of course, again, it depends on your life. Okay, so let me just show a couple of applications before we just really turn to the main topic of today's lecture, which is the introduction of contact invariance. So, what are the little applications? So here's a proposition. So here is a knot K in S3 given with 4-ball genus positive. So remember what a 4-ball genus is. We just have D4 and the boundary S3, and there is a knot, and we can just put all kinds of surfaces which are in D4 and intersect the boundary transversely, and we just compute all the possible genera and we take the minimal one. So suppose a knot with G, I will just abbreviate it to be G, although usually G denotes the cipher genus, but now we will stick to the 4-ball genus. And suppose that HF of S3 2G minus 1 K is some group A. So it's some vector space of some unknown dimension. Then HF of S3 when you do n surgery on K is equal to, or isomorphic to the vector space A plus Z2 to the n minus 2G plus 1. So the lesson is that somehow, what you can do is somebody gives you a knot and you do all kinds of positive surgeries on it. And for a certain while, all kinds of interesting things happen. But after a while, somehow, nothing really interesting happens. Once you raise the surgery coefficient by 1, you will pick up an additional Z2. So somehow, things stabilize.
This is for n larger than.
Oh yeah, n larger than or equal to 2G minus 1. Good point, thank you. Yeah, otherwise, these negative dimensions are this physics stuff. Okay, how to actually prove it? The proof will take basically one line, so it will be done by induction. So proof, induction on n, or if you teach it to like high school students, and in fact we are doing induction on n minus 2g plus 1. But let's take induction on n and we start with 2g minus 1. For n equals 2g minus 1, it's okay. So let's do an inductive step. We should start so this is our surgery triangle, right? The rule is that you do whatever surgery and then you have to put one higher surgery here and then you have a triangle. Okay, but luckily we have an induction. So first of all, we know that it's Z2. Oops, it's Z2, this guy. And we have the inductive step that it is A plus Z2, and now I have to put n minus 1 here, so this is n minus 2g. And here we have what we have to prove. But now we realize that this map is in fact 0. Why is it 0? It's 0 because of the adjunction. So let me just elaborate on that little piece a little bit more. So what is really happening? So here is our S3, and this is D4, and then we add the two-handle. The two-handle along the knot K, which has genus, 4-ball genus G. So this is a genus G surface, right? We can just cap it off with the core, and so we get sigma K with genus G and self-intersection given by n minus 1, the framing coefficient. And then we are done. Why? So what was the adjunction formula? That if fx of s is non-zero, then C1, what did I do? C1 of s evaluated on sigma plus sigma square should be less than minus chi, right? And we just plug in everything. Here we have n minus 1, and we can compute the minus of the Euler characteristic, which luckily will come out to be 2g minus 2, plus something which we don't know, but it's an absolute value. If I wrote the absolute value, did I? Let's hope I did. If I didn't, then it's your turn. And you just flip back and write the absolute value. So there is an absolute value missing. Then, obviously, by assumption, this is false, meaning that there is no spin-C structure for which the induced map is non-trivial. So their sum should be 0. So the adjunction just gives that this is 0. Whenever you see a 0, you should be happy, because instead of having this, it looks like a short exact sequence, but it's not. It's a long exact sequence rolled up. But if this map is 0, you eventually have a short exact sequence. We have this. So where did I start? Yeah. And another nice thing about using field coefficients, then you don't have to worry. The dimensions will just add up, and you will get our statement. Is it clear? So we didn't do too much, right? We just used the adjunction inequality, and we got this. So let me just give you a corollary of this this proposition. Okay, a little corollary. If there is a positive n, so
So I know nothing about format poles. Why is the push off of sigma k not equal? I mean, why don't you have to pay attention to the interior? Why is it just the disk?
So the interior where? Here?
No, inside.
This is not a disk. This has some genus.
Yeah, so that's sigma k punctures.
Yes, and then you add the disk.
And it has some push off, and it might self-intersect.
Why this is the question?
Yeah.
Okay, good. So, I mean, the way you can see it is that you can just move, say, you can just find another representative of the same homology class. For example, taking not this genus minimizing surface inside D4, but take a Seifert surface which lives completely inside S3. And the two surfaces will intersect each other exactly in their linking number. Okay? So you know, the disk will arrive to S3 in the framing curve, in the curve which specifies the framing, and it will intersect the Seifert surface exactly in the number of framing. Does it answer that? We can work on that a little later. I swear that it's true.
Now I'm really worried. Could you?
So, if there is an n such that S3 of nk is a length space, then that's good, because for length spaces we actually know what the Heegaard Floer homology is, so we can just use this argument and compute what A is, the dimension of A, and we get the following corollary that hf of S3mk is actually Z2 to the m for every m which is larger than twice the four-ball genus minus 1. And I just make a little remark that if you remember, Peter already explained that this is actually equivalent to say that hf of the three manifold with any spin seed structure is just Z2. And this is what he called an L space. Strictly speaking, L space was defined using Z coefficients, so this is a Z2 L space. So this is sort of the simplest possible Floer homology you can imagine. But luckily, we know some knots for which we get a length space sometimes, right? We were careful enough to go through that nice computation of Kirby calculus last time, and we know that all PQ torus knots have such a surgery. So this just says that if n is at least PQ minus P minus Q, then hf hat of S3 with surgery coefficient n on the PQ torus knot is just Z2 to the n. And where did I get this number from? This is exactly 2G, the four-ball genus minus 1. And notice, actually, the equality is sort of a hard theorem, that this is exactly the 4-ball genus. But we don't really need that. We just need that this number is at least twice the 4-ball genus minus 1, which can be achieved by just giving an example of a curve. So, you know, we are not using the Milnor conjecture or any solution of that. Okay, let me just add one more line to this. Namely, that in fact, there is a theorem which is not much more harder to prove, and it goes in the following way. If there is an n such that S3n of k is an L space, so notice we didn't really use the fact that we are surgering a length space. We just used its Heegaard Floer group, how it looks like. So suppose it looks like a length space. It's a Floer homology length space. Then HF, then S3R of K is an L space for every R, which is now supposed to be a rational number and bigger than 2g minus 1. So the only difference is somehow we can leave the word of integers and we can go to rationals. Of course, you have to see the point that the surgery triangle works only for integer surgeries, right? So somehow we have to use the triangle in a more sophisticated way. It's not much more complicated. You just have to put continued fractions in the picture, and I don't want to go through that. Let me point out one more thing, which I wanted to point out earlier, but then I forgot. But it's never too late. Namely that we have these maps, fx, going from hf hat of y1, t y1 to hf hat of y2, right? The induced map by a cobordism. And we always say that this homology and that homology, and when you are talking about homologies, then the induced maps usually respect the grading. And unfortunately, in this theory, that doesn't hold. So first of all, it can happen that you just take a homogeneous element. You just take psi from one spin C structure, let's say T1, and nobody guarantees that, in fact, its image will be homogeneous. Somehow, fx is a sum of a whole bunch of homogeneous maps, but itself it's not homogeneous. So somehow things are a little more complicated. Or for example, suppose that they all have absolute Q grading, and you take an element of degree d, and you just take its image. Its image might be a sum of elements with various degrees, and a priori we have no idea how to compute these degrees. So the warning is that things are not always that simple as they should be. Okay, so there is a little example I would like to tell you. So why is it good for? I don't know, but you know, you can make all kinds of computations. So for example, let me just write down a triangle. So let's take K to be the left-handed trefoil. You should be aware of the distinction between the right and the left-handed. So this is the left-handed trefoil. There is the right-handed one. Now, yeah. You know, strictly speaking, I should draw it with my left hand, this one, and with my right, that one. That would be too much. So let's take the associated triangle. So we take S3, then we take S3, and I use framing -2. I do -2 surgery on the left-handed trefoil. The triangle says that here we have to take -1 surgery on the same guy. okay? And then we come back. So this induces a surgery exact triangle where we have Z2 from here. What is the Heegaard Floer homology of this guy? So so what is Heegaard Floer of S3 minus 2, or actually minus n, left-handed trefoil? It's the same as Heegaard Floer of S3n, right-handed trefoil, because there was a rule which said that HF hat of y is isomorphic to HF hat of minus y. And mirror imaging the knot and reversing the sign of the surgery coefficient just turns the 3 manifold into itself with the reverse orientation. But now for this we can just use that corollary, and we have to remember that the four-ball genus of the trefoil is 1, so this is just Z2 to the n if n is at least 1. We just substitute back, and the assumption for m is just, it should be at least 1. Okay, so let's put it in here. So here we have a Z2 square, and here we have a Z2. And this is an exact sequence. Now, it only needs a moment of thought to realize that it can happen only in one way, which means that this map should be 0, this should be injective, and this should be surjective. So this is one way of getting information about the maps in various triangles. Either you use some other triangles to compute the groups, and then you have your interesting triangle, and the groups themselves sort of force the maps to behave in a certain way, or vice versa. You use another triangle to compute the groups. And of course you might ask, why is it so interesting? And the answer is that it's not interesting yet. But hopefully by Friday it will be, you know, one of the most interesting triangles ever. Here's a little exercise. So let's call this map F, G, and H. Show that H equals 0 by a junction. So by this I mean try to figure out how this cobordism might look, and find a torus of square plus 1, which also forces the map to be 0. You know, this is just to have a little practice, if you wish. Any questions? Because now we can start our lecture for today after this little preparation. It's never too late. So now comes what I promised at the beginning. So now we would like to sort of merge these words, and I would like to give you a short, rapid introduction to the contact invariance. Of course, we will not finish it today, as you might be surprised, but so this will be the topic of next lecture. So suppose we have a contact 3 manifold. Then Heegaard Floer, whatever, theory comes with an extra feature. Today, Peter introduced you the knot invariance. And the knot invariance can be turned into a contact invariant using the correspondence of contact structures and open book decompositions. So Heegaard Floer theory associates to it an element in HF minus y. It will be sort of clear why we have to take minus y here. The best way to think about it is, instead of Heegaard Floer homologies, I should write Heegaard Floer cohomologies here, but they happen to be isomorphic by Poincare duality to HF minus y. The construction will sort of be much clearer. And again, so in the remaining 3 minutes probably I will just tell you the basic features of this invariant, and next time I would like to prove some of the statements I will list right now on the board. So the most important statement is that it is a well-defined invariant of the isotopy class of the contact structure. So So it's an invariant of psi. It will not be so apparent from the definition because the definition will rely on a chosen compatible open book. And we have to show that it's independent of the open book. But we know what we have to do. We have to worry about positive stabilizations. And this is what we will do. First property. Second property. This element, in fact, lives in the spin C structure induced by the two-plane field. Remember, spin C structures are just equivalence classes of two-plane fields. A contact structure is by itself a two-plane field, so it naturally induces a spin C structure, and the spin C structure corresponding to psi will be denoted by T psi. And this element lives in this. Moreover, if C1 of psi is torsion, then the invariant will live in HF hat of minus d psi minus y t psi, where this is this framing invariant I was talking to you yesterday, corresponding to the two-plane field. More precisely, d psi is 1/4 C1 square xj minus 3 sigma minus 2 chi for xj almost complex 4 manifold with a boundary y psi. So this theorem just tells you where the invariant lives, and let me just tell you the basic properties. Actually, there is one more statement I would like to tell you and two more corollaries. If L is a Legendrian knot and YL, psi L, is equal to +1 surgery on L, or along L, inducing cobordism X. Remember, whenever we do an integral surgery, we actually induce a cobordism X. Then, and now the rule just tells you how the contact invariant changes under surgery, and it just says that this is what happens. If you take the same cobordism and flip its orientation, then the contact element will be taken into a contact element, and then finally corollaries. If y psi is over twisted, then cy psi is 0. If y psi is Stein-fillable, then the contact invariant is non-zero. And finally, if YL psi L, there is no final, okay? We'll do that next time. It's too long and not so interesting. The point is that this invariant is a perfect invariant to detect tightness. If you can convince yourself that the invariant is non-zero, then by line 1, you immediately see that it should be tight. And you see that you have good chances for all Stein-fillable structures it is non-zero, and hopefully we will get something much finer. We will get an invariant which detects tightness without being fillable. And hopefully by Friday, 3 o'clock, you will be also convinced about that statement. But today, despite the fact that we only started the lecture, we have to finish it. Okay, so this will be the topic of the next lecture, to define, to convince you about the invariance and prove this theorem, and then the two corollaries will be just easy exercises. Okay.